In chapter number 4, we will basically cover the combinational logic circuits. In combination, there are two types of logic circuits. Number one is combinational logic, and number two is sequential logic. In combinational logic circuits, the output basically depends upon the current inputs only. There is no memory element involved in the combinational logic circuits. Also, the output basically depends upon the current inputs. But in sequential logic, the output depends upon current input and previous output. So it must involve a memory element, so that the memory element will store the output, the previous output, and there is a feedback path in sequential logic too. So the example of combination logic circuits are adders, subtractors, code converters, and the examples of sequential logic circuits are counters, registers, etc. So first of all, we will cover the first combination logic circuit, that is a half adder. So basically, in the design of any combination logic circuits, some steps are involved. Number one is that you have to first define the inputs, the number of inputs and the outputs, and the second step is that you have to write a truth table which will define the logic of your given statement. And at number 3 is that you have to simplify the outputs according to the truth table using the simplification methods, that are the Boolean algebra or the map method. It means that you can simplify your outputs by using Boolean algebra or the map method. Now, so the last step is that you will draw a circuit based on the your simplified outputs and that you have derived from the mapping or the Boolean algebra method. So first of all, for half adder, we will define the number of inputs and outputs. Suppose in half adder, basically you have to add 2 bits in binary, that is that the number of inputs are x2 or x or y. You can define any variables for the inputs. So we have defined xy here for inputs. So basically you are adding x plus y. So for x plus y, you have to define the number of outputs also. So there will be 2 outputs for x plus y, and the 2 outputs are c and s. So for example, and for the next step, we will define a truth table. So there are total 4 possible combinations for xy 0 0 0 1 1 0 and 1 1. So 0 plus 0, in this case the sum is 0 and the carry output is also 0. For 0 plus 1, the sum is 1 and the carry output is 0. For 1 plus 0, the sum is 1 and the carry output is 0. And for 1 plus 1, the sum is 0 and the carry output is 1. So for the next step, we will basically write the expression, the simplified expression for c and s, for carry and sum. So from this table we can directly write the expression for c and s. So c is basically equal to x into y, and s is basically equal to x prime y plus xy prime. So this is basically the XOR logic, or simply the XOR of x and y. So you can write XOR y. Next and the last step is that you will use logic gates to implement these outputs. So this is the sum output and this is the carry output. The sum is basically XOR of x and y, and c is basically the AND of x and y. So you will use AND gate for carry and XOR gate for sum. Next is full adder. So in case of why it is called a full adder, because it is made up with the combination of 2 half adders. Basically we have 3 inputs in a full adder circuit. We are adding x plus y plus z, and for this also there will be only 2 outputs, but because for 1 plus 1 plus 1, c and s are enough, and it is 1 1. So for x, y and z there will be 8 possible combinations. and for 0 plus 0 plus 0 the sum is 0 and carry output is 0. 0 plus 0 plus 1 sum is 1, carry is 0. 0 plus 1 plus 0 sum is 1, carry output is 0. For 0 plus 1 is plus 1 is basically 1 0, 2 or 1 0. So in this case sum is 0 and carry output is 1. 1 plus 0 sum is 1 and carry is 0. 1 plus 1 sum is 0 and carry output is 1. 1 plus 1 is again 2 or 1 0, so sum is 0 and carry is 1. 1 plus 1 plus 1 is basically 3 or 1 1 in binary, so sum is 1 and carry output is also is equal to 1. So next we will draw map for C and S separately. So for C first, we will put ones at the specific positions of minterms that we have defined. So we will write ones here and we will form grouping of ones, so that there will be 3 possible groups of 2 ones. So C will be according to the map, C is equal to yz plus xz plus xy, or directly from the truth table you can write the minterms that at which the value of C is 1. So C is basically equal to x prime y z plus x y prime z prime plus x y z prime plus x y z. So taking the terms like z and z prime common, here we have taken the z common and in brackets we have x prime y plus xy prime, and when we will take xy common we have z plus z prime. So it is equal to z into x or y. This is expression is equal to x or y, and z plus z prime is equal to 1. So we have xy here. So again we have drawn a truth or map for S output, and in this case we can easily see that there will be no grouping of ones. So we will directly write all the minterms related to S, and in this again we will take z and z prime common, and in brackets we have xy plus xy prime is plus x prime y prime, which is basically x nor of x and y, and x nor is complement of xor. So we have written z into xor of xy plus z prime into xor y. So this is basically xor of x, y and z collectively. So by using these expressions for C and S, we have drawn a circuit, a collective circuit for full adder. So in this you can easily see that we have used 2 XOR gates for S output and 2 AND gates and an OR gate for C output. So basically 1 XOR and 1 gate AND gate is a half adder, another XOR and an AND gate is another half adder. So basically a full adder can be formed by using 2 half adders and an OR gate. That's why it is called full adder, and the previous one is called a half adder. So next is half subtractor. You have to basically find x minus y. So in this case you will need 2 outputs again, one for borrow bit and one for difference. So for x minus y, you will have 4 possible combinations of x and y: 0 0 0 1 1 0 1 1. So 0 minus 0, the borrow bit is 0 and difference is 0. For 0 minus 1, you have to borrow 1, and when you will borrow 1 you will have 1 0 minus 1. So 1 0 minus 1 is basically 1, difference is 1, and borrow, as you have borrowed 1, so you will have a borrow bit of 1. So for 1 minus 0, difference is 1 and borrow is 0. For 1 minus 1, difference is 0 and borrow is also 0. So by using this table we have written expressions for borrow and difference. Borrow is equal to x prime y and difference is equal to x prime y plus x y prime, which is again XOR of x and y. So simply from this circuit you can see that difference is equal to basically sum output of half adder, and borrow and carry have a difference of x and x prime. So you can easily draw a circuit from these expressions for a half subtractor. Next we have full subtractor. In full subtractor, basically you have to perform x minus y minus z. In this case again you will need two bits, one for borrow and one for difference. So 0 minus 0 minus 0, difference is 0, borrow is 0, 0 minus 1, difference is 1, again you have to borrow 1. So 1 0 minus 1 will be equal to 1. So difference will be 1 and borrow is 1. 1 minus 0, difference is 1, and so for 0 minus 1, basically for 0 minus 1 you will have to borrow 1. 1 0 minus 1 will be equal to 1. 1 minus 0 will be again equal to 1. So difference is 1 and borrow is again 1. For 0 minus 1 you have to again borrow 1. 1 0 minus 1, and again 1 minus 1 will be equal to 0 and borrow is 1. 1 minus 0, difference is 0 and borrow is 0. 1 minus 0 minus 1, 1 minus 1 is difference is 0 and borrow is 0. 1 minus 1, difference is 0, borrow is 0. 1 minus 1 is equal to 0 again. 0 minus, for 0 minus 1 you have to borrow 1. 1 0 minus 1 will be equal to, difference is 1 and borrow is again 1. Now you will write expressions for borrow and difference. You can see that after taking z and x prime y common, you have this form for borrow: z into x or of xy whole prime plus x prime y, and for difference you have x prime y, basically x or of x, y and z. This is equal to the sum bit of full adder, and borrow and carry have a small difference like this. Here you have prime and again you have prime here. So from these expressions you can easily draw the circuits for a full subtractor. This is your assignment, that you have to draw a circuit for half subtractor and full subtractor. So next is suppose we have to design a code converter, basically, which will convert a BCD input into XS3. So XS3 code is simply obtained by adding 3 to the BCD input. So suppose as you know that BCD input has 4 bits, A, B, C and D. XS3 will also has 4 bits at W, X, Y and Z. So this code converter will basically convert BCD input into XS3. So starting from 0 0 0 we will add 3, you will have 0 0 1 1. 0 0 0 1 will be converted to 4, 0 1 0 0, and 2 will be converted to 5 in binary, and 3 will be converted into 7 using XS3, and likewise up to 9 you will write this code converter, and after 9 you will have all the don't care conditions up till 15. Up to bit number, decimal number of 15, you will have all the don't care conditions at the output like this. Okay, so the next step is that we will draw maps for each of the 4 outputs W, X, Y and Z. So first we will draw a map for W. So you will put first you will write all the don't care conditions, and the don't care conditions are basically starting from 1 0 1 0, which is basically 10. So this is don't care condition 1 0 1 0 1 0 1 1, 1 1 0 0, 1 1 0 1 1 1 1 0 and 1 1 1 1. So these are all don't care conditions. Afterwards you will write ones for 0 1 0 1 and 0 1 1 0 and 0 1 1 and 1 0 0 0 and 1 0 0 1. So you will have one group of these 8 ones, another group of these 4 ones, and these 2 ones and 2x. So the expression for this w will be equal to a plus bc plus bd. Okay, again we will write for the output x. The don't care conditions will be the same at the same positions, but number ones will be different. So it will be 0 0 0 1 0 0 1 1 0 0 1 0 0 1 0 0 and 1 0 0 1. Okay, so the grouping is basically one group, second group, and the third group of 1 and x. Okay, so the output is x is equal to b prime c plus b prime d plus b c prime d prime. Next for y, the positions for x is same, and for the after writing ones we will have two groups of ones and x here, and the last is for z. We will have ones in this position, and we will have a single group of 8 squares, which is equal to z is equal to d prime. So finally we will draw a circuit for all these outputs w, x, y and z. As you can see, these are all the outputs and these are all the inputs. So as you will apply all the combinations of a, b, c and d, you will have an access3 code at outputs w, x, y, z. You can also simplify these outputs in product of sum form as you like. It will be also considered correct if you simplify it in product of sum form. So you can either simplify your outputs in sum of product or product of sum form. So this we have covered the design procedure for combinational logic. Next we will cover the analysis procedure. So you have to solve all the end problems related to design of combinational logic.